Theo Jones from the National Lobster Hatchery to present his presentation.
Thank you, Biscuits.
Thank you.
Sorry, I got a bit confused with the time zone, so I missed the beginning, but I'm just going to load my presentation in. So our internet is a bit slow here, so I'm going to have to load it in and you're going to have to bear with me, but it should be coming in. Sorry about this.
Problem.
Yeah, is it up? Tell me when it's loading in.
Not yet.
I might have to turn my screen. Sorry, guys.
No problem.
Let me know if my camera up.
Okay. If you have a problem to share your screen, I have your presentation. It won't be as fluid as if you share it yourself, as you will have to ask me to pass the slides.
Yeah.
But if needed, you can ask me to do it.
Cool. Have you got it up now? Because I've got it on my screen.
Yes, it's good. We can see it.
Okay, awesome. Cool. So hello everyone. My name's Theo Johns and I'm a research technician here at the National Lobster Hatchery. I'm just going to quickly kind of talk today on the possibilities of using SWAC effluent within aquaculture. So firstly, who are we as a charity? National Lobster Hatchery is a marine conservation charity. We're originally set up in 2000 in response to declining European stocks, especially around Cornwall, and then a complete collapse in Norway in about the 80s and 90s. We have three main charitable outputs. The first is conservation, which is our stock enhancement program. Second is education, where we reach out to schools and also through our visitor centre in Padstow. And then research, where we conduct kind of lobster culture technique research and further stock enhancement kind of conservation research. And ultimately, the aim of this is to safeguard our lobster seafood industry, and with that, the livelihoods of the coastal communities that it supports. So very briefly, here's the kind of the process that we go through for our stock enhancement. First, with fishermen bringing in, as you can see here, what we call buried hens. This is a female lobster with all of these black eggs underneath her tail. They'll come into us and live in our systems until all of her eggs have hatched out. Once they've hatched out, she will then get given back to the fisherman, and we will have lots of larvae to rear on. So for the first 2 weeks, these will be reared in communal tanks, and then for the last 4-ish weeks, we separate them out here into individual trays because they're highly cannibalistic. And then the process ends with our release around Cornwall. So the involvement that we've had in the EuroSwac project is the fact that our lobster module down in Newlyn has been selected as a demonstration site due to its reliable and consistent supply of seawater. And we're also keen to improve our sustainability within the process as we're a conservation charity. So the lobster module is being used to assess kind of our existing ability to maintain air and water temperatures and kind of the energy efficiency of that, and then try and scope the potential of the shallow water SWAC system in this channel region. All right, so here we have our lobster module, which is demonstration site. So you can see we're set on the quay in Newlyn down here. So we've got direct access to water, and this is our brood side where all the buried hens will be hatching, and then this is our larval side. So as part of the EuroSwac project, we were asked to kind of review the possibilities of the SWAC effluent and how it could be used in aquaculture. The reason for this is because the effluent of SWAC released into the environment may differ physically and chemically to the surrounding water, and with this, it might cause negative effects on the environment when it's released. The main parameters we looked at were temperature, nutrients, dissolved gases, pH and salinity, because these are the most important ones that we monitor within our aquaculture facilities. And then we're talking generally about recirculating aquaculture systems, which is where the water is kept within a system and recirculated and used constantly until water parameters become too bad for kind of like stock's health, and then we will replenish it. So here we've got a couple of models of possible aquafarm kind of flow designs using SWAC effluent. So this one on the left is an aquafarm here that is situated right next to district buildings that would be using SWAC for temperature control. And here we can see we've got a separate pump to mix with the hot water effluent for optimal temperature control, which then can flow into your aquaculture systems. And then on the right here, we've got an integrated kind of system where an aquafarm is using a SWAC system to temperature regulate its facilities, and then it can use the effluent directly into its systems. So the first parameter we can have a look at is temperature here. Now, in aquafarms, we aim to keep temperature of the system's water as close to the physiological optimum of the species that we're culturing. Generally, we'll use heater chiller units to maintain temperature in the system's water, and these are extremely energy costly. Energy costly. So the idea for shallow water SWACs on this EuroSwac project could be to heat our systems in the winter and cool the systems in the summer using the effluent. And this is generally because in the channel region in the winter we have warmer water than the outside air, and vice versa in the summer. So although the temperature differential in our channel region is not as great as in tropical regions, where they're accessing kind of very cold 5-degree water in a tropical climate, the availability of warm or cold SWAC effluent within or very close to aquafarms could reduce a lot of energy if it's taking the dependency off the chillers. So next we can have a look at nutrients. So build-up in nutrients in aquaculture systems is generally due to organic matter, and this can be excretions from livestock, breakdown of unconsumed feed, or incoming water during abstraction. The increases in nutrient levels in recirculating aquaculture systems as they build up will become toxic and reduce metabolism within the stock and stress them highly. Within our aquaculture systems, we use water changes as in when they're needed to dilute the nutrient concentrations, and we use biofiltration methods, which use a cultured bacteria to break down the most toxic nutrients, such as ammonia. With regards to deep water SWAC, using the effluent there, the problems that we could initially see is the fact that the deep ocean concentrates high levels of nutrients, and if we're using the effluent in aquaculture systems, we could be artificially adding nutrients, and this could be detrimental to the stock's health. With regards to channel area, we don't see this as much of a problem because we'll be abstracting water for the SWAC system at shallower depths within the mixing layers of the ocean, and thus these nutrient concentrations should not be seen, though localized effects do need to be looked at. For example, sewage outflows close to your kind of SWAC abstraction pipe, because we don't want to be bringing in high levels of nutrients caused by that. We'll move on to dissolved gases. Generally, within aquaculture systems, the main two gases are oxygen for metabolism and CO2 that we look at. Similar to the nutrients, deep water SWACs will be likely abstracting high levels or concentrations of CO2, as these are held low down in the water column in the ocean. And thus the effluent from deep water SWACs could have low oxygen levels and high CO2 levels, which would not be good for stocks health. The idea that we can explore further down the presentation is using algal species to remedy this. And then, like the nutrients, shallow water SWAC should not pose the issues of high CO2 and low oxygen concentrations. Though again, local variations must be considered. For example, algal blooms near your shallow water SWAC abstraction pipe could cause depletions in oxygen and high CO2, which would not be good for your stock's health. Moving on, we'll look at pH here. Increases in CO2 are generally cause low pH, which is detrimental to organisms' health, especially when we're looking at lobster cultures, because they are a calcifying organism, and so they need a good kind of alkaline conditions within the water. As we're saying in the previous slide, high CO2 concentrations in the deep ocean will be abstracted by deep SWACs. So this is likely to cause deep SWACs effluent to have a low pH, which will be detrimental to stocks health. Then again, this should not be seen in the channel area with our shallow water SWAC, as we will be abstracting from the mixing layer, though local conditions again should be looked at. For example, dredging activities, because dredging activities near abstraction pipes for a SWAC system could bring up anoxic sediments, which will cause very low pH to be in your effluent, and this is not what you want to be inputted into your aquaculture systems. Additionally, what we found out in Newlyn is we should monitor the pH over the course of a year, as in the summer, naturally we're abstracting water at a pH of 8.2, and in the winter we are having pHs as low as 7.7. So just natural variation throughout the year will occur as well. Moving on to salinity, maintaining constant salinity levels in aquaculture systems is optimum for optimum growth and health of stock. The only problems we could see with salinity could be due to evaporation. So if we're abstracting deep cold water at 5 degrees and then it's warming up to about 30, you could have evaporation occurring, causing hypersaline conditions within your effluent, though the design of the SWAC system should not allow this because it's a closed system, so it should prevent evaporation. With regards to shallow water SWACs, the salinity should not pose an issue in that regard as well, though conditions such as halocenes in the summer months, which is a freshwater kind of layer on the surface that we know to occur in the channel area due to a shallow continental shelf, could cause low salinity to be abstracted, and thus if you're using that in your aquaculture systems would not be beneficial. So brief overview of the water quality parameters that we've looked at. So shallow water SWACs that we're using on this EuroSwac project should pose a lot less issues compared to deep water SWACs, and this is generally because the water abstracted in shallow water SWACs is much closer in water quality to that of the environment where the common marine aquaculture species are found. And then also, if we do see water quality issues within the effluent standards, aquaculture procedures should mitigate against this. Aquaculture species are found. And then also, if we do see water quality issues within the effluent standards, aquaculture procedures should mitigate against this. So as I said earlier about possibly using algal species to remedy negative water quality in SWAC effluent. The idea could be that algal species could be, that SWAC effluent could be circulated within algal species tanks. And during this time, the algal species can kind of consume the CO2 and produce oxygen through photosynthesis, and then also feed off the nutrients and remedy the negative water quality parameters that we could see. Also, algal species generally have a greater range of water quality parameters that they can maintain healthy in. This will enable the more valuable animal stocks to be cultured in the best water quality possible, whilst also adding another stock onto aquaculture facilities. Here we've got a brief overview of European aquaculture. And then all of these numbers we're expecting to increase into the future with higher food demands from kind of the globe, and then also increasing pressures on the fishing industry to create sustainable methods. So the potential expansion of channel aquaculture in the Channel region. We do believe that shallow water SWACs, like our EuroSwac project, has the potential to utilise the thermal effluent from the system and utilise it for the growth rates, food conversion rates, and increased survival rates. These benefits will be limited to the warmer summer months, and thus aquaculture producers may return to rearing at lower temperatures during the colder months, or they may use their heater units in these warmer months, but they should see over the year a reduction in energy. In addition, we should be able to increase or expand the species that can be exploited. So if we're able to cheaply access higher temperatures in the water, we might be able to start rearing more tropical species here in Europe. So what's next? What's next for the lobster hatchery is the fact that we're going to see if SWAC has the potential to keep broodstock or our broodstock well managed, and also accelerate our larval output by shortening their development times through our systems. We believe the Lobster module will provide valuable insight into the suitability of SWAC technology for meeting these temperature requirements, and then also insights into kind of SWAC use for general aquaculture facilities, and also potential stock enhancement projects similar to ours. So yeah, that's me. Sorry, I think I ran over a little bit, but thank you ever so much for listening, everyone.
Thank you, Theo. Does someone has some questions? Okay, so we have a question from Martin Brown.
Yeah.
Is it possible to use a less emotive word than effluent?
Yes. it's a bit late now. Sorry. Yeah, what it would be outflow, I suppose. Though the emotive word of effluent could be used to support kind of a need to look into its possible environmental implications. Yeah, so I think effluent is probably quite a good word in that, because it will raise awareness into the problems that it could cause that need to be looked at.
Okay. Is there other questions? I believe we don't. So you were pretty clear in your presentation. Thank you very much.
Oh, that's lucky. Thank you very much, Biscuits.